we have looked at a number of different elements of the charges, moving conductors, and so on. What I want to go through with you today, to start off with, I'm going to look at this phenomena called electromagnetic induction. I would normally do this as a class presentation because there are a couple of things in here which need a little bit of visual movement, and you'll see I'm going to use left hands, right hands, and so on. And it's a bit difficult to try and do that over this medium. But the concept is important because the other part of the lesson is going to be looking at the next topic, which is alternating currents. And it would help to understand a little bit about electromagnetic induction before we cover alternating currents. Now, tomorrow's lesson will be on transformers, because when you come in on Thursday next week, we will actually be doing a lab where you'll be working in groups and you'll be looking at transformers, how they work, how we measure, and so on. So it's logical that we'll do that in the lesson before you get on to the topic that we're going to cover. So to start off with, let's have a look. Move on. Let's have a look at the topic, which, I'm sorry, I have a second PC here in the room, which I'm trying to make sure is functioning so that I can see actually what I'm presenting, which is sometimes useful. So I can now see the presentation as it's appearing on the other screen. Now you've seen a diagram, something similar to this, and I've demonstrated for you in class what happens when we place a coil of wire or a piece of wire that contains electrons inside a magnetic field. And if instead of what's here, we placed a battery, the battery allowed the flow of electrons, which meant that this wire moved upwards. In this example, we have no current, we have no battery, we have no source of power. But if we place this coil of wire or this conductor here inside the magnetic field, every time the wire cuts through the magnetic lines of force, it induces a voltage in this meter. So as I move this piece of wire through this magnetic field, every time I cut through one of these lines of force, I induce a current inside this piece of wire, and we get a movement on this meter. Now in this meter here, you can see the movement is to the right side because this wire is being lifted upwards into the through the magnetic field. If I move the wire downwards, so move it down through the magnetic field, I will get a deflection in the opposite direction. It doesn't matter whether the wire is moving or if it's the field, the magnetic field that is moving. Provided one of them is moving, we will get a change in this current that's induced just here. Now, there are several ways that we can increase the current that's induced. The first one is we can move the wire faster. So as I move my wire out, I can move it quickly up through the, you can't see, I take my piece of wire, where is my piece of wire? Oh, it's gone now, but it doesn't matter. I take my piece of wire, move it up quickly, and it will move through the magnetic field. So the faster I move this, the greater the induced EMF. Anybody guess or suggest what else could I do to increase the induced current in this piece of wire? So I've said moving it faster is one way. What else could I do to increase the current induced and flowing through this piece of wire? Any guesses? Nobody. Increase the magnetic flux density. Great, absolutely right. If I make this magnet here stronger, I can use a stronger magnet. I get a bigger deflection on the meter. There's one other thing that I can do. Any guesses what that last thing would be? Think about what affected the movement. When we talked about the electrons, we could increase, for example, the length of this piece of wire. So if we increase the length of the wire, the easiest way to do that would be to use a coil of wire, lots and lots of turns of wire. So we could use a coil of wire and increase the number of turns. And that in itself would mean there are more current carrying conductors existing inside this magnetic field. So whenever I cut a magnetic field, the faster I do it, the stronger the magnetic field, or the more pieces of wire that I use, the greater that induced EMF. And that is called electromagnetic induction. Now you recall previously we talked about Fleming's left-hand rule. The left-hand rule, let me just make sure you can see that. The left-hand rule shows you if I have a current flowing through the second finger, a magnetic field flowing through the first finger, so I place inside a magnetic field a current carrying conductor, I get a motion that could be displayed by this thumb. So if I change the direction of the magnetic field, I get then an alternate movement. Fleming's right-hand rule can be used to predict the direction of the induced current, this time if we know the direction of the force and the magnetic field. And this gives us something similar to what we had before, but this time using the right hand. So here we have in this direction, we have the magnetic field represented by the first finger. The second finger represents the current, and that will result in a motion vertically. So now what we're going to do is if we apply this to our previous diagram, So if I look at this now with Fleming's right-hand rule, I've got my magnetic field, I've got my current, and I've got motion. So if you can see just here, I have my hand now. My finger, first finger, is pointing from north to south. The motion is directed upwards, as you can see from the thumb, is pointing upwards. Which direction results? Well, the second finger shows the direction of the current, which means that it's going in this direction through here. So the current is flowing around in this direction. So I now have a representation which will tell us, and this is sometimes known as Fleming's right-hand rule, is sometimes known as the dynamo rule. It's what we use for generating a current. It's how we describe what is happening when a current flows or is induced into a coil of wire, such as with a generator. Now let's try and explain this. I've said to you that it happens, and yes, it happens because we are moving a coil of wire or a charge carrying conductor in a magnetic field. So now what I can do is, if I imagine this electron is going to move across the screen just here, the magnetic field is actually going into the screen. So this blue ring here is a circular area with the magnetic field going into that screen. So let's press play and see now what happens. So the magnetic field is into the screen. The electron is moving horizontally here, and the force that results is downwards. So we've got an original motion causing the electron to move downwards. So the magnetic field exerts a force on the electron, and it's both in the direction against which the original motion was traveling. In other words, the electron will start to move downwards. What does this physically look like? Well, if we place a piece of wire inside that field, what it means is all the electrons get pushed down towards the bottom of that rod. They are forced downwards. So the rod is moved across this field. The electrons that are in here are forced downwards. So it causes a buildup of charge at the bottom of this rod. And this charge is balanced, of course, by a positive charge at the top. And this is called the induced EMF, electromotive force. Consider the opposite direction. So as long as this is moving, the electrons go in this direction, causing a force downwards, positive, negative, as the conductor is moved across the magnetic field. In the opposite direction, when the conductor is moved in the backwards, the electrons are forced to move upwards. So we get this flow of current now. Remember the difference between conventional and electron flow. Electrons go internally conventional flow goes from positive to negative. So we have a conventional flow around this circuit. If there is no motion, if this bar remains still inside the magnetic field, nothing will happen. There is no movement, so the electrons remain where they are. There is no magnetic field, there is no induced EMF present, so no current will flow through this device. Now, there are a number of additional slides. I'm not going to cover those during today because they are relevant for induction, of course, and I think one or two of you are using some of these principles for your GYAR. Please make sure, if you wish to look at this, have a look and see what the remainder of the presentation is about. I am not going to cover that during today. What I am going to talk about, though, for the remainder of this lesson is the next topic, which is that of alternating current. Right. Now, we've talked over a couple of lessons, and you had last year during your introduction to direct currents, to electricity, you taught about DC. What was direct current? If you were to describe it, what would you call it? Direct current is anybody? Silence in the ranks. Great, thank you. Flowing in one direction only. So if we consider unidirectional, good. So it is to do with the flow of electrons. And an oscilloscope, which is what I've shown you, I think, during the last lesson, is a glorified voltmeter. When I switch this on, I can measure I can measure the voltage across this resistor. You probably saw these devices last year. So now direct current flows in this circuit, as you can see around here. This component is called the resistor, and most devices inside a house, I have a torch here, I have batteries, I have various different things, all of which use this flow of electrons to control some form of circuit. The electrons, of course, flow in one direction, only one direction. And this value, or this voltage, is measured as a constant value. So if I take a battery just here, 1.2, 1.5 volts, that voltage stays constant. Of course, over time, it will slowly disappear, but it does remain constant. And what you can see on this oscilloscope just here is, if you look at the scale, and let's just say every one of these squares vertically is a measure of 1 volt. Now, I don't think I can change the circuit here, no. But if I turn this off, you'll see that the voltage disappears. Turn it on and the voltage goes from this 0 level at the center to 1, 2 volts. Let's now consider what will happen with an alternating current. What you can see now, an alternating current is what we just produced using that induced EMF, that voltage that was produced by induction, moving a coil through a piece of wire, through a magnet, causes a current to be induced. And what you can see on here, this time, the electrons are moving not in one direction, but backwards and forwards. They are constantly switching their direction and producing what we can see on this screen here, a sine wave representing a maximum voltage and a minimum voltage down here. Now this sine wave, which is produced, has a constant amplitude. Its maximum and minimum remain constant as long as this field is changing up on the top here. So let's now consider an alternating current. That alternating current can be represented in a form like this. Each one of these squares on this scale represents a constant voltage. So each one of these divisions might represent 1, 2, 3, 4 volts. Similarly, 1, 2, 3, 4 across the bottom. So what we have here, there are 3 things that we can measure with an alternating current. Namely, you can measure the peak to peak, the value from here to here. So we can measure the peak to peak value, which is top to bottom. We can measure the peak value, which is this value to the top of the peak. And the final one, which is not intuitive, is what we call the RMS voltage. In an alternating current, there is an average value of the voltage. What would be the average between this value and this value just here? Just write up on your chat messenger. What's the average voltage between the peak value here and the peak value here? Great pair, yes. Great, pleased to see it. The value, of course, is 0. So at the center here, we're halfway between the top and the bottom. So we've got a 0 value as the average voltage. But mathematically, it's possible to do one thing. If we square a value and then take the square root of that number, we can get another type of value. What we actually end up doing is we take the square root of the mean squared voltages. So if we have, let's just say this voltage is +1, +2, plus, whoops, I don't want that one. Doesn't matter. +1, +2, +3, +4. -1, -2, -3, -4. So if I square the plus value I get +4. I square the minus value. What value do I get now? I also get +4. So what I've got is two peaks, both of which are 4. So if in theory I take the square root of that one plus that one, I should get the average between them. And the RMS measure is the average magnitude of this voltage. And the RMS value, because if I invert this and put this on this side, you'll notice that there are gaps in between here. So when I take this peak and put it up there, I end up with a ripple effect. But there is still some part of this which is not filled. So the root mean square value of the voltage is the peak voltage divided by the square root of 2. Don't worry about where the square root comes from. Mathematically, it's easy to calculate. But for you, I'm just asking you to take that the RMS voltage will always be less than the peak voltage. So the voltage peak divided by square root of 2 gives you the RMS value. Now that is true for voltage. Let's look at the next part, which is to consider the current flowing through an electrical circuit. And to investigate voltage, we use an oscilloscope. But we also know that voltage is proportional to current. Remember from last year, V equals IR, Ohm's law. Voltage is proportional to current. The constant of proportionality is the resistance. So if voltage is proportional to current, it means if I increase the voltage, I also increase the current. So what I can now say is that the current RMS is equal to the peak current divided by square root of 2. But the equation for RMS power is a little different. Remember last year, you calculated power is current times voltage. P equals I times V. But this is for peak values. So the peak power is equal to the current peak times by the voltage peak. What we can see is that the power is current times voltage. So power RMS is current RMS times voltage RMS, which equals I RMS is equal to I peak divided by root 2 times by voltage peak divided by root 2, which tells us now that the RMS power is the peak power divided by 2. In other words, it's half the peak power. And that's an interesting phenomena because it tells us that power is not conserved equally as with a direct current. So flowing a power circuit, and if you think about it, the power is changing from positive to negative, positive to negative, and so on. It's constantly changing. Therefore, peak RMS power is regarded as half the peak power. Now, I've given you quite a few things to think about, so I'd like you now to answer some questions. You'll need the formula VRMS equals V peak divided by square root of 2. So let's make a start. Looking at this first graph here, what is the peak to peak voltage of this signal? Enter it please into your chat, and I'll wait until I see a number. 1. Right, good. Great. Your answer is correct. Now for the second part, I'd like you to now work out the RMS value of this signal. Remember, formula VRMS equals V peak divided by square root of 2. So now I can calculate the value of the RMS value of this signal. So again, calculate please. Please make sure that, good. Great. Representation, VRMS equals V peak divided by square root of 2, which equals V peak to peak divided by 2. So now we have the value voltage peak is peak to peak divided by 2. VRMS is 5 divided by square root of 2, which gives us 3.54. So correct. This time we have a signal that has an RMS voltage of 6 volts. What will be the peak value of this voltage? And the second part will be to show what that looks like on the measuring screen. Just be careful. I saw one answer there. Remember this time, this is the RMS voltage. And we know the peak voltage must be greater than the RMS voltage. So the RMS is 6 volts, means these two are not correct. Now, I know what one of you did, but the correct answer, of course, is 8.49. VRMS equals V peak divided by 2. So V peak is VRMS times root 2, which is 8.49. So I say one of you, I think, made the mistake. You actually did this calculation, which gave you, of course, then this answer here. So the second part, yes, second part, which oscilloscope reading shows this signal? Again, look at the values. You started off with a value of 6. So here we've got 2, 4, 6, 8. 2, 4 volts. Peak to peak is 8. So which will be the correct I think most of you have got this now. You get what we're going for. So the middle value, the second one, is the correct answer. So now we've manipulated this formula. It looks daunting because there's a square root of 2 in there, but it's not actually that difficult. If we now go to the final one, this is going to give you an idea of why, if you placed your finger inside a light bulb socket, inside a plug, you're asked to wire a socket for something. Why does mains voltage, 230 volts, hurt so much when you touch it? So it has an RMS value, the average value of an alternating current at home is 230 volts. When you calculate the peak voltage, and I think again you're getting the right picture, 325.3 volts will be your maximum voltage. Think about this now. The maximum voltage is 325. The minimum is also 325. So the peak to peak voltage is 650 volts. That's why it would hurt if you actually stuck your finger in the socket. You are giving a huge jolt of energy from almost 650 volts peak to peak value, which of course your body probably wouldn't react too kindly to. So which signal does this represent? Again, have a look. 100, 200, 300, 100, 200, 300, 100, 200, 300. So which one are we looking at? And again, I think you've got the picture. Well done. That gave us a clear look at each of these phenomena. Now, we have managed with most of this to give ourselves an opportunity to see how to write an alternating electrical current. But there are still a number of things that we need to look at. It's important that we understand how we calculate peak to peak from peak voltages. Let's see if that is correct. A term you'll see here, and I want you to answer these, all 5 of these. Send me this solution in the chat, please. The drift velocity, if you remember when I showed you the induction, the electrons are free to move up and down inside a conductor. And in some instances, you'll find that that is the case. In some instances, it isn't the case. An insulator has no free electrons. So an insulator is a material which doesn't allow electrons to move through it. An insulator stops electrons, so it has a very, very, very infinitely high resistance. it stops anything flowing through it. Copper wire has very low resistance. Copper has lots of free electrons. Most impressive, of course, is gold. Gold has huge number of free electrons. Not exactly what we would want to make wire from. I suppose it would be if you were looking for the perfect world. And indeed, any of you that are hi-fi enthusiasts, you've probably heard of gold-plated connectors that are used in hi-fi. They give the best transmission from a piece of wire to a piece of equipment. So gold-plated connectors are used. Again, part of the recycling of mobile phones. Gold is used inside mobile phones to coat certain connectors. Now, if I took my mobile phone apart, I'd probably find a millionth of a gram of gold in there. But if I took 1 million mobile phones, I might get a gram of gold out of those phones. So, of course, this is part of the reason for recycling, part of the reason for recapturing usable materials from something like an extinct or broken product. So have a look, please, through these 5 questions. Enter your answers: 1, true or false; 2, true or false, and so on, through to the end of the numbers. So I have none so far. Oh, let's have some solutions, please. Question 4. The number of charge carriers in a metal is a relatively low number. Are there charge carriers in a metal? Is that true? Is a metal like an insulator? If there were no charge carriers, it would be an insulator. But most metals tend to be insulators or conductors. Good. Couple more moments and then good. Okay. Let me just put this back on the screen. To finish, I would like just to share with you this final interaction. And this is really now the type of thing. I'll turn off the generator. What we have here, this is a typical AC generator. So we have here a coil of wire, and this coil of wire is inside this magnetic field. So as you'll see on this side here, this coil is going to move upwards through the field. This coil on this side is going to move downwards through the field as this rotates. So let's start it rotating. What you can see in here, and I'll stop this at different points, is we've got to a point here where, let me just see, can I move it back? Or let's move it. As we are moving this coil of wire through this magnetic field, at this point just here, this is moving at its maximum cutting rate through these horizontal field lines. So there are my magnetic field lines, and the current flows in this object, as you can see just here. So we've got a magnetic field from north to south. We've got the current induced by the motion, and I'll keep this moving round now. So we'll get to a point around here where this coil is not cutting any of the magnetic lines of force. As you can see, this is outside, this is outside, so the resulting voltage just here is 0. And if I rotate this through 180 degrees, I go through the maximum, so this is moving up through this field, down through this field, keep going again to the top, and again we've got no cutting through the magnetic field lines. So the only thing we have at this point, whoops, what have I done? How did I do this? Not quite sure what's happened here, but I appear to have... See if I can start it again. Right, so you can see it now. Yes, you can see it. So again, if I just go back to this model, I can start this rotating, get to the maximum value, the 0 value just here, no cutting through the magnetic field, move through, as you can see, this side is rotating downwards, this side is rotating upwards to the maximum value, as you can see on here, on the negative side of the coil. This one, keep moving again, up to 0 and down to the negative, the maximum on the other side. Now you'll notice that each of these coils has a connection. Has a connection onto this former. You can just see here, there is a connection on the one side of the coil to this former, and the other side of the coil just here onto this former. So these two are completely independent. You can see starting here, going around this circuit and out to here on this circuit. So we now have a device, and if I just let it play now, which gives us, by moving a coil through a magnetic field, an alternating voltage which goes from positive to negative, no value given necessarily in this, but giving us the field that we need to travel through. Right, now, I wanted to stop this. And I've lost my... Now, all of these things that we've been through today that I have started talking to you about are the terms that we've looked at. Everything has linked for us: moving charges, electric fields, magnetic fields. We've now completed all of the parts of the jigsaw that make up electromagnetic radiation. So possibly we will make a start. I don't think we're going to manage it before Christmas. We will do the lab during the next lesson, as I've already said to you. We will then continue on Friday, the lesson you've all been looking forward to. And then the week following that is project week. So I think that we will then have an ideal start in January. Hopefully we'll be in school, but it may well be that we're still on distance learning. And we will then make a start on the next section of the course, which will be looking at waves and wave properties. Right, any questions for today's lesson, please? let's see if anybody wishes to ask anything or anybody has anything that's not clear. Any questions? I'm just copying